Even if general relativity has led to considerable advances in our understanding of gravity, gravity still seems to hold many of its secrets, and physicists are still searching for the famous gravity transmission intermediary known as the graviton, or any other theory that might help us understand how gravity is transmitted, in addition to the dissociation between general relativity, the main theory of gravity, and quantum physics, and the theory that explains the behavior of matter on an infinitely small scale. Certain phenomena, such as dark energy and dark matter, also seem to defy general relativity and presuppose a possible modification of general relativity. The notion of space-time introduced by general relativity also makes it difficult for anyone to understand gravity intuitively and appears to be a mathematical construct rather than a physical phenomenon. This lack of a deep understanding of gravity makes any intuitive understanding of gravity almost impossible. In this video, we'll try to see if changing a few assumptions in the space-time model will enable us to gain a more intuitive understanding of this phenomenon. To achieve our goal, we'll start by simplifying the space-time model of general relativity, and it's precisely the notion of space-time that makes the general relativity model non-intuitive. So if we can separate space from time, we might be able to understand this theory better. To achieve this goal, we'll start by admitting a few hypotheses that may seem a little bizarre, but which will allow us to reach our objective by transforming the liberation velocity formula, which we'll try to write as a function of gravitational time dilation and the speed of light. Gravitational time dilation is the phenomenon that causes time to pass more slowly under the influence of gravity. For example, two twins can be of different ages if they are subjected to different gravitational forces. The formula for gravitational time dilation is the root of 1 minus 2 gm over r times c squared, where g is the gravitational constant, m is the amount of mass that exists in the space under study in kilograms, r is the radius of the space studied in meters, and c is the speed of light in meters per second. The liberation velocity is the minimum speed an object must have to escape the gravity of a star or any gravitational force, and its formula is the root of 2 gm over r. The mathematics we're going to use are very simple and don't require advanced mathematical knowledge. First hypothesis: instead of a universe with 3 spatial dimensions and 1 temporal dimension, we'll assume that our universe is made up of 4 spatial dimensions and 1 temporal dimension. This assumption is no new concept in modern physics and even forms the basis of string theory, which assumes 7 additional spatial dimensions rather than just 1. The idea of additional dimensions is not complicated, and to understand it, we need only imagine a 2-dimensional universe in relation to our 3-dimensional one. This universe would resemble a giant sheet, mainly 2-dimensional, with a 3rd dimension so fine that the beings living on this sheet-like universe wouldn't even realize it existed. In such a universe, all movement will be in both directions, left, right, and forward, backward, since the 3rd dimension is so small that beings living in such a universe won't be able to move up and down and won't be aware of its existence. It's the same thing for the hypothesis of the 4th dimension of our universe. We'll assume that it's so thin on a quantum scale that we're unaware of its existence. So, according to this hypothesis, we're living in a 3-dimensional sheet of a 4-dimensional universe, 3 ordinary dimensions, and a quantum scale dimension not discernible by our traditional resources. The second hypothesis is that our 3-dimensional universe, with a 4th quantum scale spatial dimension, moves at the speed of light in the 4th dimension when empty, while the parts containing mass move in proportion to gravitational time dilation multiplied by the speed of light. This hypothesis is also predicted by general relativity, which stipulates that all stationary objects move at the speed of light in space-time. So for a value of gravitational time dilation equal to v, the speed of our 3-dimensional universe in the 4th dimension is v times c, where v is gravitational time dilation and c is the speed of light. There are 2 types of time dilation, one caused by gravity and the other by speed. For this explanation, we're interested in gravitational time dilation, and its formula is root of 1 minus 2 gm over r times c squared, where g is the gravitational constant. M is the mass of the celestial body part of the studied space, r is the radius of the studied space, and c is the speed of light. Multiplying gravitational time dilation by the speed of light gives us the speed of our universe in the fourth dimension. The result is the root of c squared minus 2 gm over r, that is approximately the speed of light minus the baryonic matter density of the space times the gravitational constant. So, from this speed, we'll try to guess the speed needed to escape the gravitational force of a massive body and reconstitute the escape velocity, knowing that the escape velocity formula is root of 2 gm over r. So, as mentioned, and in accordance with our hypotheses, the speed of a part of the universe in the fourth dimension is v times c, where v is gravitational time dilation and c is the speed of light. This allows us to calculate the slowdown of a portion of space occupied by a mass in comparison with empty space moving at the speed of light as indicated by our hypotheses. So the deceleration of a massive body in the fourth dimension is c minus v times c, or c times 1 minus v. So moving at this speed in the opposite direction to the slowdown theoretically allows us to escape gravity. It's like someone on a boat that's slowing down. To avoid being stuck to the wall behind him, he has to accelerate forward at the same speed as the boat is slowing down. But to achieve the expected result, two adjustments need to be made. The first adjustment is that we're talking about the speed of movement of our three-dimensional universe in the fourth dimension, which is not far from the speed of light. So time in this part of space is dilated because of this speed, and any action in this space will be slowed down like a film in slow motion because of the effect of speed. To correct this effect, we need to multiply the velocity required by the formula for time dilation due to speed, or what we call the Lorentz transformation. The Lorentz transformation formula is 1 over the square root of 1 minus v over c squared. With a capital V here being the speed of the part of space studied in the fourth dimension, not to be confused with the small v, which is the gravitational dilation of time. So capital V is equal to small v times c. As we said earlier, the speed of our universe in the fourth dimension is equal to the gravitational dilation of time, times the speed of light. So the necessary correction is 1 over root of 1 minus v times c, over c squared, or 1 over the root of 1 minus v squared. V here is the gravitational time dilation. The second adjustment takes into account the fact that we live in a predominantly three-dimensional universe and that the fourth dimension is a quantum scale dimension, so we can't accelerate in the opposite direction to the fourth dimension. But general relativity teaches us that our space is curved by mass in spacetime, or what we call here the fourth dimension. So for a massive body, we can exploit this curvature to go partially in the opposite direction to acceleration in the fourth dimension. Gravitational time dilation can also help us formulate this term, since it is proportional to gravitational intensity and therefore proportional to curvature in the fourth dimension. Consequently, if gravity is at its maximum, v tends to 0, and the correction tends to 1. So there's no correction at all, which is normal because our space will be completely curved in the fourth dimension. If gravity tends to 0, time dilation tends to 1 and the correction tends to double, and the correction become 1 plus v. V is the gravitational time dilation. Therefore, the escape velocity formula should be c times 1 minus v times 1 over root of 1 minus v squared times 1 plus v. It's very easy to verify that this formula is equal to the original escape velocity formula. We can rearrange the formula to have c times 1 plus v times 1 minus v times 1 over root of 1 minus v squared. 1 plus v times 1 minus v gives us 1 minus v squared. This allows us to simplify with root of 1 minus v over c squared and have c times root of 1 minus v squared, We replace v by its value, the root of 1 minus 2 gm over r times c squared. C times root of 1 minus 2 gm over rc squared. The 1 minus 1 cancels out, and we simplify the c to the exterior of the root with the c squared in the root to have the original escape velocity. This demonstration allows us to confirm that to escape the gravity of a massive star, we need to go at the speed of slowing down of this star in the fourth dimension, multiplied by the Lorentz transformation, since our acceleration is made in a universe that moves at a speed close to the speed of light, multiplied by another factor, a plus v, to take into account that we can't go in the opposite direction of slowing down, but that we can partially use the space curvature in the fourth dimension caused by gravity to partially go in the opposite direction of slowing down. The question now is, why do massive bodies slow down in the fourth dimension? The answer can be found in quantum mechanics, and more precisely in the Higgs mechanism. Simply consider the Higgs field as a fourth-dimensional field. It's a field that exists in the fourth dimension, just as the Earth's atmosphere is a three-dimensional field in comparison with a two-dimensional universe shaped like a giant sheet that's mainly two-dimensional. The idea is quite simple. Our universe is mainly three-dimensional, with a quantum scale dimension that moves in a larger four-dimensional universe filled with a substance called Higgs field, which interacts with massive bodies and forces them to slow down their movement in the fourth dimension, a slowdown that manifests itself in space curvature and time dilation, and the greater the mass, the greater the slowdown. This idea allows us to understand the idea that physicists often repeat to explain the Higgs field when they say that without the Higgs field, a particle moves at the speed of light and therefore cannot have mass. It also allows us to understand the idea that we developed today, which states that a massive body slows down in the fourth dimension, so it's the Higgs field, through its interaction with massive particles, that slows down massive bodies and curves our space in the fourth dimension. This new way of understanding gravity allows us to answer questions posed by modern physics, such as, why does the speed of light appear everywhere in physics formulas? According to this explanation, the speed of light is no longer an arbitrary constant of physics, but the speed at which a part of the universe moves when empty. It also confirms that gravity is not a fundamental force, but rather a manifestation of the interaction of baryonic matter with the Higgs field. So defining gravity as the curvature of space-time is no longer sufficient, and the full definition would be that gravity is the slowing down of three-dimensional space with a quantum scale fourth spatial dimension in the fourth dimension as a result of the interaction of the massive particles occupying this space with the Higgs field. The curvature of space and the slowing down of time are both manifestations of this slowing down. As you can see, this idea links general relativity to quantum physics through the inclusion of the Higgs field, which is at the origin of the gravitational interaction, and through the fourth dimension, which is a quantum scale dimension that could eventually explain certain non-intuitive behaviors on the quantum scale. This explanation of gravity also gives us an understanding of the two forms of time dilation, gravitational time dilation and time dilation due to velocity. As explained above, time dilation is due to the slowing down of three-dimensional space with a quantum scale dimension in the fourth dimension, as the flow of time is proportional to this velocity. In the case of gravitational time dilation, it's the interaction of mass with the Higgs field that slows down the velocity of an object in the fourth dimension, and consequently dilates time. In the case of time dilation due to velocity, it's the object's kinetic energy that slows its progress in the fourth dimension, and the principle that it's more difficult to displace a moving object than a stationary one is in effect here. The fact that a body is moving in our traditional three dimensions slows down its movement in the fourth dimension. This explanation allows us to establish a relationship between the speed of light on the one side and the speed of a part of space, or an object in our traditional three dimensions on the other, plus the speed of that part of space or object in the fourth dimension. The ratio is, Speed of light squared is equal to the speed in the fourth dimension squared plus the speed in the three dimensions squared. Applying this formula to gravitational time dilation becomes speed of light squared equals speed of space in the fourth dimension squared. That is, gravitational time dilation times the speed of light all squared plus the speed of this space in the traditional dimension squared. That is, escape velocity squared. Stop the video if you want to check this equality. Applying this equality to time dilation due to velocity gives speed of light squared is equal to the speed of an object in the fourth dimension. That is, time dilation due to speed times the speed of light squared plus the speed of this object in our traditional three dimensions squared. For this equality too, verification is easy. Just stop the video if you want to check it. In a second video, we'll take a look at how this can help us to explain dark matter and dark energy.